It's well known that the primary costs and losses in petroleum refining come from sudden failures of equipment. A distributed control system, DCS, supplies comprehensive information on the process and operation modes of the equipment. However, machine health during operation escapes the attention of operators who continuously change the process modes while controlling the process plant. For sustainable and reliable operation, it is necessary to provide operators with timely, unbiased information on how the operation mode affects the equipment's health. The information and early diagnostics of defects can allow operators to identify a failure and allow people to eliminate future issues at its emergent stage. The conventional approach to keeping reliability of machinery at a certain level hasn't changed over the last 70 years. It is based on three primary pillars: a safety factor, which is the ratio of a machine's structural capability to actual applied load; operational discipline of personnel, which is always striving to do the right things by the right ways; and failure recognition capability, which is an ability to predict failure before it happens. At the beginning of the reliability era, the primary method for extending reliable uptime of machinery was increasing the safety factor. However, significant over-increasing of structural capability to actual applied load led to rising costs of machinery, which negatively impacted consumers' interests. Since the 1950s, several approaches to providing the reliability of machines were developed and implemented, such as preventative maintenance, proactive maintenance, reliability-centered maintenance, and others. But all of those approaches have two common issues: poor statistics for machinery lifespan and the human factor. To confine the influence of those factors on reliability since the 1970s, the main focus moved to increasing a failure recognition capability. Until now, scientists, engineers, and practitioners attempted to point out an instance of a machine's failure to be able to prevent its breakdown using different instruments and method. We could name that era analog reliability because people strive to increase the reliability by evolving all pillars and making them stronger, more clear, and more precise. Digital reliability emerged at the beginning of the 1990s when PCs were used for reliability tasks for the first time. Since that time, computers play a significant role in the evolution of reliability theory and practice because of several reasons. They compute complex functions very fast, process large amounts of data, and deliver information for better decision-making to different places and to many different people simultaneously. In order to explain the key distinction of digital reliability from all known reliability approaches, first of all, let's consider what's the difference between conventional machinery diagnostics and early diagnostics. Diagnostics is a process of identification of malfunction that consists of a few steps. The first and most crucial step is collecting data about machinery health, which contains the choices of data type, data sources, data volume, frequency of data gathering, and the tools to do that. Any mistake at this step severely affects the diagnosis, making it either wrong or untimely. The process of diagnostics has two distinct errors: an error of static recognition and an error of dynamic recognition. The error of static recognition appears when a failure cannot be detected because either the wrong non-destructive testing (NDT) method is utilized or the proper NDT method is used in the wrong way. The error of dynamic recognition appears when a failure cannot be detected and prevented because the time period between measurements exceeds the time it takes for a defect to emerge and influence on the equipment. The later a defect is identified, the greater the consequences and expenses are. The shown curve represents the dependency of costs and losses by fault detection. Within its lifespan, equipment undergoes three stages of degradation: nonlinear wear, exponential wear, and critical wear. These are divided on the curve by the red dots. It is critical to identify the instant a defect begins because it is the best opportunity to intervene and prevent a serious accident and possibly a shutdown due to equipment failure. While diagnostics itself is a process of defect detection, and it doesn't matter when you find out an issue, early diagnostics is a process of defect prevention because that saves time to react accordingly. Existing solutions, such as protection or condition monitoring systems, are focused on confining consequences, not preventing breakdowns. DCS merely shows the failure, at best correctly starting the emergency shutdown to minimize the consequences of equipment failure. It does not identify the fault at an early stage of degradation and provide urgent actions to be taken to eliminate it. If the protection system alarms, the breakdown almost happens. Even new AI software solutions work at the end of the exponential wear stage because the AI analyzes the same parameters that protection, condition monitoring, or control systems measure. Moreover, almost all condition monitoring systems require an expert to interpret. Without that interpretation, the operator cannot understand what should be done to prevent an impending failure. This is the main reason why most breakdowns and accidents happen on the night or weekend shift. The expert is not on duty at the facility. To not only prevent failures but even repairs and maintenance, we need to identify the emergence of issues in the nonlinear wear stage, when destructive forces are just beginning to degrade the equipment. With the real-time diagnostic COMPACS system, an operator doesn't need to be an expert in vibration analysis to know how and when to react. Diagnosing the health of every piece of equipment in a facility in real time and delivering precise, timely prescriptions to operators 24/7, the system identifies these destructive forces at an emergent stage. Thus, safe and reliable operation becomes a reality. I would like to introduce the real-time diagnostic COMPACS system, which monitors all types of rotating equipment, including centrifugal and piston compressors, pumps, air coolers, and more. The system monitors state of every piece of rotating equipment within the facility and diagnoses each of them every 3 to 5 minutes. The diagnostic station is located in the control room and using a single hardware and software platform can be integrated with the DCS, PI, SAP R3, and other systems over either Modbus or OPC interfaces. The SCADA-type field bus gathers proper data for physics-based AI that transforms sudden defects into gradual ones and warns personnel by prescriptions what actions needed to be taken to prevent a failure and keep a machine running. The monitor mode is the most important mode of the system because it displays all machinery in the unit in one glance. This is customizable to any particular facility. The cursor shows the section with the worst condition and correspondingly to the machine with the worst condition. On the top left, this display shows the various parameters measured. The prescriptions are displayed at the top right corner. The different color coding represents different states of health. Red means unacceptable condition, yellow represents a machine needing actions to be performed, green indicates the machine is operating safely, and gray represents a machine out of operation or on standby. The physics-based AI identifies the various types of faults of rotating equipment. Here we have a list of faults found in centrifugal machines. And over here, you see the types of defects found in reciprocating compressors. The COMPACS system detects most of the failures of rotating equipment with a probability of 97 to 99%. The physics-based artificial intelligence utilizes scientifically proven knowledge on degradation of various nodes of different machines. If the system identifies patterns of features associated with a certain class of defects and malfunctions, artificial intelligence selects the algorithm and determines the fault and its degradation stage. This is not a case of machine learning or predicting failure. The system knows the defect exists if the diagnosis is given. Several refinery units can be combined into the plant diagnostic network, COMPACS-Net. In COMPACS-Net, you can see information about every unit equipped with the system. If you move the cursor to the logo of the particular unit, you see details of the equipment health. If you double-click on the logo, you can remotely connect to a particular system and view the issues. However, any system is just a tool. In order to gain digital reliability benefits, it is necessary to engage all personnel in the reliability process. This is why we have developed the technology of safe, resource-saving operations and maintenance of machinery. This methodology is presented here. As you can see, there are 3 information loops to ensure the reliability of equipment in operation. The first loop is shown on the right and shows the operator's involvement in reliability. Operators are the only people in the entire facility who could prevent degradation when it emerges. The operators must be responsible for the reliability of the equipment they control. This is the reason we promote the operators-driven reliability approach. When prescriptions are received, they need to take urgent actions to improve the equipment's health. They could do this by themselves, call the maintenance department, or schedule contractors. The second information loop delivers the same information simultaneously to the maintenance department. The maintenance team becomes capable to schedule in advance and perform even a complex repair. There are no more reactive and repeated repairs because all maintenance activities are scheduled based on the actual technical machinery condition. Moreover, both operators and the maintenance team assess the maintenance quality immediately using the COMPACS system's prescriptions as feedbacks for those actions. The last loop is information for managers. Management staff receives, in real time, objective information on the equipment state, operators' contributions to the reliability process, and quality and timing of maintenance actions performed. The COMPACS system ensures transparency for all those involved in reliability. Personnel working in a transparent environment always try to be more effective and efficient by paying more attention to the equipment's reliability and by entrusting and cooperating with each other. Now, I would like to show the guidelines on how to attain the benefits of digital reliability's implementation. After the COMPACS system has been installed, management, operators, and maintenance teams get on the same page. All see the same unbiased picture of real-time equipment health. The first 6 months operating with the COMPACS system are the most crucial for the reliability project. The paradigm shift can be seen in the next two charts. Here you can see the monthly quantity of repairs that are performed in maintenance workshops, and next is the quantity of maintenance actions that are performed by operators according to the system's prescriptions. In the first 6 months, the maintenance department completed about 15 to 17 repairs per month. In the same period, the operators, using the system's prescriptions, increased the quantity of maintenance actions from 30 to 60 per month, which as you can see stabilized at this level. After the maintenance activity stabilized, repairs dropped to 1 per month, significantly improving the reliability of rotating equipment in the unit. In the next set of charts, you can see examples of the maintenance according to the machinery state. Here you can see the slow increase in the vibration parameter associated with a bearing defect. The system generated an action-required alert, check bearing, and erase. The bearing was slowly deteriorating, and after 27 days, the pump was taken out of service for repair. Armed with the knowledge of the actual condition of the pump, there was time to schedule the repair and switch to a standby machine. Upon inspection of the pump, a crack was revealed in the inner race of the rolling bearing. This illustration shows an example of fast bearing deterioration that cannot be prevented by anyone except operators. There are 12-hour trends of the acceleration and velocity measured on the front bearing of the pump. When the acceleration increased from 12 to 24 meters per second squared, the system generated an unacceptable condition alert. The COMPACS system prescribed check bearing lubrication and check bearing cage. At the time of the unacceptable condition alert, the vibration velocity parameter remained acceptable for another 18 minutes. Only after 18 minutes did it rise from 2.7 to 27 millimeters per second. Only with this early diagnosis of the issue were the operators able to proactively switch to the standby pump and prevent an emergency shutdown. The next step to improving reliability is eliminating the root causes of failures. Here, we can see that 11 machines in a facility with around 200 machines generate 80% of maintenance orders. If you eliminated the root causes of these failures, the reliability of the facility would greatly improve. Now, this is an example of eliminating the root failure cause of an exhauster. In the before box, you can see the exhauster was operating in the action required state. The maintenance team was carrying out repairs at points 1, 2, 3, and 4. Using the COMPACS prescriptions, check for imbalance and check for looseness. This includes tightening screws and aligning the exhauster. As you can see, those repairs did not yield the desired result and the machine kept running in the action required state. At point 5, the impeller was dynamically balanced, and the health improved considerably. It also moved to an acceptable state and its vibration decreased significantly. The root cause of the exhauster's failure was impeller imbalance. Eliminating the root cause not only reduced the risk of unpredictable failures at the facility, but confirmed an upgrade to the existing maintenance procedures to include dynamic balancing. After eliminating the root cause of failures, the most important and most expensive step is next, eliminating bottlenecks. When a facility is designed and constructed, there's little concern with using the best engineering solutions. Most engineering companies use technical solutions that are just good enough to get the facility running. Construction companies use the cheapest acceptable materials and contractors. Owners also don't want to overpay for the best solutions. As a result, there are several bottlenecks that confine uptime. Revealing and eliminating those bottlenecks is very important because it leads to more efficient facility operations. I will present an example of how to remove bottlenecks. Here, you see two trends of different vibration parameters for piston compressors. The upper trend shows deterioration of the valves. As you can see, on average, every week the compressor faced valve issues. With the incorporation of the COMPACS system, it became simpler to compare different parameters and figure out the root causes and bottlenecks. When the reliability team compared the trends of valve deterioration with the trends of hydraulic shock, they confirmed the correlation. After each hydraulic shock, valves quickly deteriorated. Further investigation revealed that there was no filter between the compressor, and it was dirty gas causing hydraulic shocks and valve deterioration, thus poor compressor reliability. They kept 2 standby piston compressors to keep the facility continuously running. The compressor was repaired once a week until a gas filter was installed. Since the filter was installed, the issue no longer was a bottleneck for the unit. But to be honest, the reliability team was trying to convince management to fund this solution for about a year. This table shows the key performance indicators that best lend themselves to evaluating the performance of the COMPACS system. If we look at these, we can see the best world indicators for petroleum refineries and the KPIs for one of our best customers, the Omsk refinery. The Omsk refinery has been operating with the COMPACS system for over 26 years. You can see that for each indicator, the KPI is much better when using the COMPACS system. I'd like to focus your attention on 2 particular KPI, reactive maintenance and availability. Reactive maintenance is around 0% because if you know exactly what kind of issue a piece of equipment is having at an early stage, you do not need to wait till the issue turns into a failure. You can proactively eliminate it at the best possible time. Not everyone achieves this, but the aromatics unit at the Omsk refinery did. They have really achieved on-demand planned maintenance. But our largest accomplishment is the unit's availability, which is over 99%. The Omsk aromatics unit operated for 3.5 years with 0 downtime. The real value which digital reliability brings to a petroleum refinery comes from several sources. First, that concept allows us to prevent accidents and shutdowns. According to analysis of several trustworthy sources, in 2017, an average amount of annual refinery losses due to unscheduled shutdowns was significant. Thus, by transforming sudden defects in machinery into the gradual ones, refiners can avoid most of the incidents and corresponding losses. Another source of value is extended uptime. By decreasing turnarounds outage and extending average uptime from 91 to 99%, an average refinery can add a significant amount of additional profit. Finally, an average U.S. refinery spends quite a bit on the maintenance annually, which could be reduced significantly by employing the COMPACS system. As you can see, implementation of the COMPACS system at an average U.S. refinery could have an enormous effect on uptime and, as a result, profitability. Summarizing the aforementioned information, it would be necessary to list the bullet points of digital reliability, which is based on 24/7 real-time machinery diagnostics. In order to reach desirable outcomes in safety and uptime, digital reliability requires proper infrastructure for collecting useful data from trustful sources. It does this by using the SCADA structure and the physics-based artificial intelligence, which operates by invariance to extract information on time, and a plant diagnostic network for simultaneous information delivery to all levels of decision-making from operators and engineers to managers. The COMPACS system is the only one that meets those requirements and assists refiners to make the reliability paradigm shift to implementing the technology of safe resource-saving operation and maintenance of machinery. It brings timely and objective information about machinery health, operators' involvement, reliability, and maintenance quality. Moreover, it provides financial benefits which exceeds investments in the solution by at least 10 times, provides confident safety of process operation, and generates prosperity for all those involved. Digital reliability shifts the focus of the reliability process from predicting failures and guessing when to perform repairs to detecting emerging destructive forces and preventing the evolution of defects that degrade equipment health and lead to its failure. I would like to emphasize once again a simple thought. A sudden breakdown is only sudden because nobody monitors its evolution. If your monitoring system detects destructive forces at the initial stage of degradation, operators receive an instant prescription of the defect to fix and avoid equipment failures, recovering the equipment lifespan by merely changing the process mode. Therefore, if the diagnostic system detected machinery degradation in real time and distributed the information among those who were involved, the safety, reliability, and uptime of the facility would become a reality and depend directly and only on those who operate, maintain, and manage it.